In this video, we're going to introduce a magnetic device known as an inductor and focus on a particular property known as self-inductance. Here's an overview of the video. We'll first review the concept of magnetic flux. This is important because we need to understand how magnetic flux is generated around a magnetic device in order to define its inductance. And then we'll work through a number of examples to reinforce the practical way in which one can determine the inductance of a device. So let's first review magnetic flux. Magnetic flux phi is related to magnetic flux density B through this surface integral. And because we know that magnetic flux density is related to vector magnetic potential A through this curl operation, we can see that magnetic flux can be then computed using a surface integral of the curl of A. But because of Stokes' theorem, we know that a surface integral can be turned into a contour integral. And so instead of having to do the surface integral of B dot ds, we can evaluate the contour integral of A about a contour C, that is the outer contour that S is bound by. So this can be particularly convenient if we happen to know the vector magnetic potential of a device that we are trying to analyze, because a contour integral might be simpler than a surface integral. Okay, so with magnetic flux defined, let's revisit an example magnetic device that we've analyzed previously using Ampere's law, and that is a toroidal inductor shown on the bottom left. So this inductor consists of a magnetic core material, which is in the shape of a donut. That magnetic core material could be a ferromagnetic material, or it could just simply be air. And then we just have some sort of form that we can wrap these wires around. But the basic idea is that we wrap these wires around this magnetic core, and then we apply a current to the wires. So if we use the right-hand rule and analyze the magnetic field produced by, let's say, the lower wire here, we can see that the magnetic field or magnetic flux density is going to be generated in the direction shown. And if we repeat this over the core, we can see that the magnetic flux density is going to want to go upward at this particular point. And if we repeat this for all of these other turns comprising our inductor, we can see that each one of these turns produces a magnetic flux density that flows through the core in a clockwise direction. So if we attach a coordinate system to our diagram here, so let's say we overlay a coordinate system like so. Then let's say the upward direction is the x direction and the horizontal direction is y. Then with this particular choice of coordinate system, this clockwise direction is the phi direction. So we could write the magnetic field as going in the phi direction, as you see on the right here, by attaching a phi unit vector. Now, the magnitude of the magnetic field is Ni over 2 pi r. This is from analysis of Ampere's law of this particular toroid, which we'll not repeat here. And then we can calculate the magnetic flux density B. And we know there's a constitutive relationship between B and H, which is given by this expression here. So we simply multiply by mu to get B from H. And mu refers to the magnetic permeability of the core material. So if our core material is, let's say, a ferromagnetic material, mu will be very, very large, and we will end up with a B field that is quite a bit larger than it would be if we had just used air or a non-magnetic material. So then we can proceed to calculate the flux. So the flux is, for the purposes of our inductor, the flux is generated wherever the B field exists, but the majority of the B field exists in the core. And so if we considered a cross-sectional area of the core, which is going to be a circle, if we slice our donut and have a look at the toroid here, this is going to be a circular cross-section, and this is what S refers to. So when we calculate phi, the magnetic flux density, this surface S here in the integral refers to the cross-sectional area of our magnetic device here through which the B field would flow. And you can see that the B field here, or the H field, is normal to that surface S. So it would be fairly easy then for us to carry out this surface integral B dot ds because we have an expression for B And if we know how B varies across S, then this surface integral can be carried out. We can begin to answer what flux links each turn of our coil. This is quite crucial to the definition of inductance. So we're going to introduce a quantity here known as flux linkage. Flux linkage, we're going to use a symbol, Greek letter lambda, this is capital lambda, which is defined as a product of the number of turns in our coil and the flux density, flux phi that links each of them. So we find this by first computing the flux phi, which we did in the previous slide, and then simply multiplying that by the number of turns, and that is what we call flux linkage. If there was only one turn in our inductor or in our toroid, then N would be 1, and the flux linkage would be simply equal to the total flux. So now we can define inductance, or in particular a quantity called self-inductance. We're going to give it a symbol L, and it is defined to be the flux linkage, which is lambda or N phi, divided by I. So we should end up with a quantity for inductance that does not depend on I. And this makes sense because any sort of circuit parameter like inductance or capacitance or resistance shouldn't depend on current. My inductor, if there's 10 amperes flowing through it, shouldn't exhibit a different inductance than if there were 100 amperes flowing through it. The units of inductance are henries, and of course we can attach SI prefixes to that, so we can have nanohenries, picohenries, microhenries, and so on. Okay, so now let's look at a particular example of a inductor called a solenoid. A solenoid is just a fancy name for a coil, and we can see some examples of solenoidal coils in the picture here. So as you can see, we've taken some wire. This wire is actually insulated. The insulation is clear, so you can't really see it here, so that the individual wires aren't shorting out with each other. And we can wrap them around a magnetic core, which in this case looks like to be a ferromagnetic core. And you can see that we can have various configurations here, different diameter cores, different number of turns, which affects the length of the coil, and so on. So a cross-sectional view of this coil is shown over on the left here. Two examples are shown, one where the coil is very loosely wound, and one where the coil is very tightly wound. But to understand why the magnetic field looks the way it does here, it's useful to start with the loosely wound coil on the left. And if we imagine the wire coming in and out of the page, because we're taking a slice through that coil, we can see that we have a wire coming into the page here, coming out of the page here, and this alternates between the coil coming out of the page on the left and going into the page on the right, and so on. Okay, so now we can use the right-hand rule to look at the individual magnetic field produced by each wire. And so wrapping our fingers around, let's say, this lower left wire that's coming out of the page, we can see that the magnetic field is going to circulate as shown in the sort of anti-clockwise direction. And same thing for this wire coming out of the page, and same thing for this wire. And so they contribute to a magnetic field that's downward to the left of the coil, but upward to the right of the coil. If we analyze the wires that are going into the page on the right, again using our right-hand rule, we can also see that they produce magnetic fields, in this case, that are going in the clockwise direction. And so that's going to lead to a magnetic field that's downward on the right, but also upward on the left. So because the coil diameter is not very large, we get very, very high magnetic flux density B within the confines of the coil. And that's really the magnetic flux density that we're interested in. The B field is rather weak outside of this coil. And this is particularly true if we tightly wind the windings of the coil, which you see on the right. So we get very, very high density field lines here. So our magnetic flux density is going to be very, very high within the coil itself. This is going to be particularly true if we introduce a magnetic core. So just for example, I'll overlay one over here, and this is again a slice through our magnetic core. And if it has a high magnetic permeability, then the B field is going to be very, very large here. So we're going to analyze this solenoid. We should attach some dimensions to the solenoid to make things a bit clearer. So the first thing that I want to define here is the radius. So the radius of this core is A. And we need to also define the length of the core, or length of the inductor over which the wires exist. And we're going to call that L. So let's assume that there's wires spanning the entire length of L. Okay, so we're going to proceed to analyze this inductor now. This integral formula that's shown here is taken from a table of integrals. This indefinite integral will help us with a particular integration that's going to arise when we have to analyze this coil. So let's draw a side view of this inductor. So begin this down here. Let's draw our core again. From the side, again, it's going to look like a rectangle. And let's draw our wire. So our wire is going to come out of the page, let's say on the left, and go into the page on the right. And let's just draw a bunch of wires. Imagine that we are wrapping wire around this core. We're going to end up with a picture like this, and this is going to carry on over the length of our coil. So again, this length here is L. Okay, so these windings here can be thought of as a superposition of loops, right? Each pair of wires going in and out of the page, it can be seen of as a loop. So if I focus my attention on, let's say, just the bottom row here, we can think of this as a single loop. Okay, so let's this particular coil on the bottom can be thought of as a loop. And we have analyzed loops before. This is a magnetic dipole, and we can draw the current flowing like so. And if we were on a point on the loop axis, we used the Biot-Savart law previously to find the magnetic field at this point that is on the axis. So we can write the magnetic field at this point. And I'm not going to rederive this result here, but it is in the numerator we have I, the loop current, times the area of the loop. So collectively the numerator is the magnetic dipole moment. And in the denominator we have a term 2 pi a squared plus z prime squared to the power of 3/2. Z prime refers to the z location of the loop of interest. So it's somewhere along the z-axis at a location z equals z prime, and that is what that's referring to. And obviously, since we have many, many loops comprising our coil, we need to know the z location of every one of those loops, which is what we're calling z prime. So what we're going to do next is we're going to focus our attention on a very small length within our solenoid, which I'll highlight here. And this length is very, very short. It's dz prime. It's an incremental length of solenoid. So let's write that down. dz prime is an incremental length of solenoid. And it's containing a product of n dz prime turns, where n is the number of turns per unit length. Okay, so its units are per meter. So for example, I might say that there's 10 turns per centimeter, and so if my coil was 2 centimeters long, I have 20 turns total. Now, dz prime is a very small number, and so we're using this product to represent the number of turns within that very, very short segment, dz prime. That's useful because then we can work out the differential contribution of the coils contained within dz prime to the magnetic flux density field. and dB is just related to dH through our constitutive relation, which we discussed before. And we have a formula for H shown on the upper right. So here we're going to replace, that's for a single loop, but obviously we have multiple loops here. We have NDZ prime loops. So we need to make a modification to that. So first we need to multiply by mu, because we're concerned with the B field, and we're going to place I with I times NDZ prime. Then we still have a pi a squared and a denominator that remains the same, 2 pi a squared plus z prime squared to the power of 3/2. Now before we go too far, these pi's in the numerator and the denominator are going to cancel out, so let's not track these anymore. So our variable of integration here is z prime. So we need to integrate over the entire length of the inductor. So if we return to our picture on the upper left here, we might say that the origin of our inductor, let's sketch a coordinate system on the inductor. So let's say that the inductor is on an axis here, and again, the radius of our inductor is A, and the bottom of the inductor might be located at z equals minus L over 2, and the top of the inductor might be located at z equals plus L over 2. So our variable of integration, z prime, needs to be integrated from minus L over 2 to L over 2. So let's write out our integral over here. B is the integration of z prime from minus L over 2 to L over 2, and then we'll write in our integrand here. And again, our pi's have canceled out, so we won't write them anymore. Okay, many of these terms are constant, so we can pull them outside of the integral. So let's do that. So we have our direction, of course, and then we have mu. I is a constant. The number of turns per unit length is a constant. A squared is a constant. And in the denominator we have 2, that's a constant. So now we're integrating from minus L over 2 to L over 2 dz prime over a squared plus z prime squared to the power of 3/2. Okay, this is where that table of integrals entry comes in, because if we compare this integral that I just wrote down to what was up here, you can see it's basically identical, except that instead of x we have z prime. So we can use this particular entry to evaluate this integral. And so let's write down the result of that here. So we're going to have z hat mu I n. Now this a squared term is going to disappear, because in our entry here we can see that we're dividing by a squared, and so that's going to be canceled out, and we just have mu I n over 2. And then we can evaluate the rest of the integral. So the integral ends up evaluating to L over a squared plus L over 2 squared all square root. Okay, so there's the final expression for the B field. Now, something that would be very useful for us to note is the geometry of our solenoid. So if we go back to our solenoid, in this particular picture, it's pretty clear that the length L of the coil is much longer than the radius A. And so if we can make that assumption, we can actually simplify this expression for B. Okay, so let's write that down. If the length of the solenoid, which is L, is long, and by long we mean that L is much, much larger than the radius of the solenoid, well, then if we focus our attention on the denominator, this L over 2 squared term is going to dominate compared to the a squared term. So it's almost as if we can just cross this out if L is very, very large. And then we're taking the square root of L over 2 squared, so we're just left with L over 2. So we can write this as an approximation then, that we are left with L over 2 in the denominator, and this is pretty nice because these L's are going to cancel, and then actually these factors of 2 are going to cancel as well. So we have a nice expression here for the B field. Something that we will want to do is actually write down the total number of turns in our solenoid. So the total number of turns in our solenoid depends on the length, right? Because we know that there are lowercase n turns per unit length, and the total length is L. So if I call this n, that is the product of n times L. So rather than canceling out the L's here, let's undo that and let's just leave it like so that we can replace this product here, NL, with capital N, the total number of turns. Now I can say I have 40 turns in my inductor, and I can substitute that in here. So if we write the expression like this, then the B field is equal to, again, Z direction mu I times capital N over L. Okay, realize that I can write capital N over L as lowercase n if I wish. Okay, so now we are finally ready to compute the magnetic flux density, which is what we need for inductance. So magnetic flux density is found by integrating B dot ds over the cross-sectional area of the solenoid. So let's return to our picture of the solenoid up at the very, very top here. And we need to think about where is the magnetic flux being generated. So we see that the B field was sketched through the core, and so our core is actually cylindrical and circular in cross section. So this is our surface of integration S, right? It's going to be a circle if we look at these inductors in the picture on the right here, that surface is like across the cross-sectional area of the core. So in order to evaluate this integral of B ds, we need to know how B varies over S. And this expression that we've written for B here is really only true along the center axis of the core. B probably weakens a little bit as we move away from the center of the core. But because the B field is very, very concentrated within the core, which is what we see in these pictures here, we can treat the B field as essentially, as we walk across the cross-section of the coil, we can treat B as approximately constant. And that simplifies this flux integral quite a bit, because then B can come outside the integral. And we can simplify this as B times A if B is assumed constant over the cross-sectional area S. Okay, so an A is going to be whatever that cross-sectional area happens to be. So we can now write our total magnetic flux density as mu times I n times A over L. And that is our final result for the magnetic flux density. Next, we have to find flux linkage, lambda, which is equal to, from our definition from the previous slide, n times phi. So we're going to end up squaring n in this phi expression. We're going to end up with mu I n squared times A over L. Now we can finally evaluate the inductance of this solenoid. We take the flux linkage and we divide by I. And so we're going to be left simply with mu n squared A over L. This is a very useful expression because it tells us how the properties of the inductor are influenced by the various parameters. So just like we did for parallel plate capacitors, we can say, if the plate spacing increases, the capacitance goes down. If the cross-sectional area increases, the capacitance goes up. So can we do that for inductors? So clearly, if I increase the number of turns in the inductor, Actually, the inductance goes up with the square of the number of turns. If I increase the cross-sectional area of the inductance also goes up. It's tempting to think that as the inductor gets longer, the inductance goes down, but remember that the total number of turns is also related to the inductor length. And so your N is proportional to L. So in fact, the proportionality with the length is actually with L and not 1 over L. All right, so this concludes this first example for inductance.